Today we're going to be talking about how to solve a linear congruence. So in the last video, if you recall, we talked about how to know whether or not a linear congruence has a solution. And the points that we got to, or the determining factors, were that if the GCD of A and M divides B, so if this equals some integer, then there is a solution. And if the GCD of A and M equals 1, say this, hold on, there is a solution. And if the GCD equals 1, then there is a unique solution. So only one value of x that provides a solution. And if the GCD is greater than 1 and B divides B, then we know that there's multiple solutions. However, if I'm just going to restate it here. If this does not equal an integer, then we know that there is no solution. Okay, so we're gonna go over some examples and talk about how you can solve these problems. So we're really quickly gonna go over some of the methods you can actually use to solve a linear congruence. So one of the first ones is, and this method is kind of like tedious, is you can just kind of start to guess and check. So if we were to look at this linear congruence, one way that we can kind of start to find, I missed the congruence. One way that we can kind of start to try and find remainders is you can go through the method where you take whatever A is in this case times this. Now we'll call K some integer. So A times some integer minus M will give you a remainder. And then we can kind of just start like filling in values for K, and then we're going to need some multiple of M sometimes in certain cases. So we'll just give this value C. M is still going to be this right here, but you may get to a multiple of M, you may not. So these are just multiple integers. Um, so we can do this and we can keep going until we find B, and that K will then be X. However, um, I wouldn't really recommend it doing this way because there is a better way to do it, and that is by finding the modular inverse. So the modular inverse of A, this would be the modular inverse of A. Now, I don't want you to confuse this with 1 over A. This is just a notation for the modular inverse, okay? And the modular inverse is a number such that when you multiply it by A, it is congruent to 1 in mod M. And this is important because say we take, okay, so I'm just going to rewrite this right now. Okay, so we have this. Say we take and multiply by this. We have to multiply by both sides, remember? This side right here will just become 1. So we can just rewrite this as this, which really simplifies it and makes it a lot easier. Well, I forgot the right there. Yeah. And so this is the method we're going to be going over today by finding the modular inverse. And there is an algorithm you can use to find it called the extended Euclidean algorithm. However, we will not be doing that in this video. We'll be going over that in the next one. So we're going to be talking about this today and going over some examples and getting some practice in. Important point that I actually forgot to talk about was when to know if there actually exists a modular inverse. So with the hypothetical congruence that we've been showing, let's write this out. A modular inverse for A exists if and only if the GCD of A and M equals 1. So if the GCD, like if this GCD of A and M is greater than 1, then there is not a modular inverse. And and you'll have to guess and check to find that value of x, which does make it a bit more difficult and tricky, but it doesn't necessarily mean that it cannot be done. So this is another way to see if you can actually solve this problem with a modular inverse. If not, you will just be guessing checking, and that is tedious, but uh, I don't think you'll see too many problems like that because that could be time consuming and just, But this is just an important point. I want you to keep this in mind, and this is good to know. So, all right. So for the first example, we're gonna be going over this equation. We're gonna solve this linear congruence, okay? So if you recall, our first step should check if there actually is a solution. So we're gonna do, in this case, the GCD of A and M will just be the GCD of 7 and 12, which equals 1. Okay. And this tells us that there exists a unique solution since this equals 1. Okay. So now we know that some solution does exist, such that x will equal some integer. Okay. So remember, we need to find the modular inverse of 7, because in this case, A equals 7. Let's go through and write these out. B will equal 5, and M will be 12. Okay, so we need to find some, if you remember, we need to find the modular inverse such that this is true. So in this case, this will be this. All right, so I'm going to cut this down, free up some room here. All right, so we're looking for some number times 7. We'll give a remainder of 1 and mod 12. So I think the easiest way to go about this is let's start naming out multiples of 12. So we have 12, 24, 36, 48, and 60. Now let's start naming out some multiples of 7. We got 7, 14, 21, 28, 35, 42, 49, and yeah, that's good for now. Okay, now we just need to find one multiple of 7 that is 1 greater than a multiple of 12. So it's definitely not going to be 7 here. This is greater by 2. It's definitely not going to be these ones. No. Yeah, this is 1 less, so no. 42, it's 6 greater, so no. Oh, we got 49. Okay, so we have, yeah, 49 minus 48 has a difference of 1. So we found a multiple of 7 that is 1 greater than a multiple of 12. That shows us that that multiple of 7 has a remainder of 1 in mod 12. Basically saying here that if we take, because this is 7 times 7, if we take 7 times 7, we're given a remainder of 1 in mod 12, right? What does this just look like? This literally looks like our definition of a modular inverse. So the modular inverse of 7, which we're writing as with this notation, quite literally actually equals 7. So 7 is its own modular inverse. Now let's free up some space and let's look at how we solve this from here now. Since we know that 7 is its own modular inverse, rewrite that actually. Since we know 7 is its own modular inverse, we can now look at this equation, right? Of 7x is congruent to 5 and mod 12. Remember, we can multiply it by the modular inverse on both sides. So this has just become 7 times 7, but remember, this simplifies to 1, so we don't actually need to think of it that way. This becomes 1x, which we can actually just get rid of the 1, obviously, and have it times, and have 5 times negative, or not negative, sorry, 5 times the modular inverse of 7, which is just 7. 7 times 5 is 35. I'll write that in the next line, though. This is what we have right now. Let me do this, and we have 35 in mod 12. Okay. Now, notice how this number is actually larger than 12. Um, when we're working in modular arithmetic, what we can do is we can actually reduce this number. So if we find the remainder of 35 in mod 12, we can just rewrite that as the answer of x because it is technically equivalent. Um, so remember recall that a multiple of 12 is 24. If we take 35 minus 24, we'll get 11. And this is actually the closest we can get, and this is actually less than 12. So that works. So now we can just call x 11. And we just solved it and found x. Now if we want to check our work, we can do that too. So we do 7 times fill in x times 11, which is 11, and see if this statement is true. We get 77 here. And if we look at the multiples of 12, one of them is 72. I'm just going to give you this answer. This is something that you can look over yourself and you can obviously go check. The closest multiple, but just think of like finding the closest multiple to 77 of 12. So the closest one is 72. And if we take 77 minus 72, we get 5. So yeah, our answer is correct, and x is equals 11 in this case. So for example 2, we're going to be solving the linear congruence for 3x is congruent to 4 in mod 7. I want you to go through the steps and try this on your own, and then just check back with my answers. And I'll give you a second. Okay, so step 1, remember, we need to see if there actually exists a solution. So we're going to find, not mod, GCD of 3 and 12, not 12, 7. These are both prime, so this is gonna just end up being 1. So we know that there exists a unique solution. Okay. Now we want to find the modular inverse of 3. So what does the modular inverse of 3 equal? Let's start going through multiples of 3 and multiples of 7. So we'll do multiples of 3 here and 7 on this side. So we have 3, we have 6, 9, 12, 15, 18, 21. We'll go up to there. We have 7, we have 14, 21, 28. Okay, we just need to find one multiple of 3 that is 1 larger than a multiple of 7, and this one pops out pretty quickly. We see 15 here and 14. So basically what we're saying right now is 3 times what number is going to give a remainder of 1 in mod 7. And if this multiple 15 is 1 greater than 14, then it's basically saying what is 3x equals 15? What is x in this case? It's 5, right? So it'd be 3x, 3 times 5 is congruent to 1 in mod 7. So our inverse is 5. Okay, so now that we found that inverse, what can we do to simplify this problem? I want you to think about it. If you said multiply both sides by the inverse, then you're correct. So go 5 times 3 times x is congruent to 4 times 5 in mod 7. Now remember, this is just going to value to 1. So we can just cancel that out. So then we're left with x is congruent to, and this is going to equal 20, 20 in mod 7. Now, I don't like how this number is larger than 7 because we can reduce this to an actual remainder of 7. The next multiple of 7 before, or the multiple of 7 before that would be 14. 20 minus 14 equals 6. So this is going to give us a remainder of 6 in mod 7. So then x ends up equaling 6. Okay, let's do a quick recap and go over what we just learned. So we just learned how to solve a linear congruence. And we went over the steps of how to do that. So let's go by step. Remember, see if there is a solution. Let's just say find number of solutions. And we do that, remember, by finding the GCD. Well, let's say this. If B is divisible by the GCD of A and M, there exists a solution. Obviously, if GCD, not obviously, but if the GCD of A and M equals 1, then there's a unique solution. Um, and if this does not equal an integer, then there's no solution. Um, using GCD of A and M. We'll just call that step. We'll say that for step 1. Step 2, find the inverse of A. Because remember that the inverse of A with this notation times A is congruent to 1 in mod M. So this will help us reduce the equation, cancel some things out, make it cleaner to work with, and easier to find B. Or to find X, technically, actually. Okay, so find the modular inverse. Step 3, multiply both sides by the modular inverse. Because like I just said, this will help reduce it, and then we'll have like a clean B value, or I guess is B times the inverse to work with that we can then reduce. So then I'll say for step 4, reduce B times A to be less than, what's this? Reduce B times the modular inverse to be less than or equal to 0. And we'll do this, but less than M. And then, yeah, that should be about it. And then basically at that point, you're done. And then just write out X equals, you know, whatever that value may be. I probably shouldn't put that. Write out answer. Yeah, and then you're done. Then you just solve the linear congruence. And yeah, so this was one way to do it by using the, write this big, modular inverse. So yeah, we just went over how to find the modular inverse and how to use that to solve linear congruences, which steps you should take to solve these problems. And I hope this helped in some way. And in the next video, we'll go over another method of how to solve linear congruences. So thank you for watching. I'd really appreciate it if you could like or subscribe. It really helped me out a lot, and thank you.